My name is Robert Dijkgraaf. I'm the director and Leon Levy professor here at the Institute for Advanced Study. Great pleasure to welcome you to this impromptu lecture by Demis Hassabis. In fact, the last time I introduced Demis was a rather imposing environment. We were in the Royal Palace in Amsterdam with the king and queen in the audience. But perhaps this is even more imposing here, since you are at the birthplace of essentially modern computer. John von Neumann building his computer here, and how wonderful to have Marina, his daughter, here in the audience, blessing this event. It's great to have you here. I think we probably all agree that we're living in an entirely exciting time of science. I like to say we are moving from the discovery of the building blocks, genes and atoms and bits, to building. If you just look at the news in the last few years, you've seen the breakthroughs like first quantum computers, CRISPR, gene technology, and of course AI and machine learning. And I think people will reflect back on this age, and particularly for the young people here, so how exciting that you were around in 2019 when all of this stuff was happening. And if there's something I think that encapsulates that enthusiasm, it's Demis Hassabis, whose career somehow mirrored in many ways the meteoric rise of AI and machine learning. I think many of you are familiar with his CV, but just mention a few highlights. He was a chess master at age 13. He developed the multi-million selling simulation game Theme Park by age 17. I think then you had to wait a year before you were allowed to go to Cambridge, where he finished with a double first in computer science. Then he started the computer game studio, Elixir Studies. Then decided that was not enough and that we had a different way to look at computers, and took a PhD in cognitive neuroscience at University College London, did PhDs, postdocs in MIT and Harvard, and then in 2010 founded DeepMind. That was acquired by Google in 2014. Demis and his team hit the headlines worldwide in 2016 when AlphaGo, the famous computer program, had his achievements. We'll definitely hear more about that. He has many accolades, was elected a fellow to the Royal Society last year. He's also a fellow Royal Society of Arts, Royal Academy of Engineering, and received a CBE for his many accomplishments. So we feel that we are extremely lucky. For us, this is also the weekend of the Board of Trustees, so I see many of our trustees here in the audience. Many of them have also very intimate, their lives are intimately entangled with computers and computer science, so I think we all are looking forward to the talk by Demis. After the talk, I will moderate the Q&A with the audience. So a big hand for Demis Hassabis.
Well, look, thanks Robert, for that very kind introduction. It's a real pleasure and honor to be here at the IAS. It's my first time in Princeton, and I've had a wonderful couple of days just drinking in the atmosphere and the amazing history of the place. And also, as all of you know, coming to appreciate what a special and unique place the IAS is. So it's a real pleasure to be here. So I'm going to talk about artificial intelligence today, and specifically I'm going to focus in on self-learning systems, which is the main area of research of my company, DeepMind. So our mission, the kind of vision behind the company when we set it up in 2010, which now seems like the dark ages in some ways, is before AI got as popular as it has today. The thesis behind the company was a kind of two-step process we thought of it as. Step one, if we can kind of fundamentally understand intelligence, the nature of intelligence, and recreate it artificially, then it should be possible, if we do that in a general enough way, to potentially use that to solve almost everything else. Now, we sometimes sort of, we actually use this in our pitch decks to VCs, and you can imagine the kind of response we might have got in 2010. But it seems pretty far-fetched. But I hope by the end of this talk, you'll be convinced that this thesis might be at least a little bit plausible. So more prosaically, how did we go about our mission? Well, we think about what we're trying to do at DeepMind as trying to build the world's first general-purpose learning system. Now, AI is obviously an old field, and it's been going on since the 1950s or before. Many of the people at IAS were at the foundation of that. And there's sort of two main approaches to trying to build artificial intelligence. In the 80s and 90s, a lot of the big projects were based around logic systems, kind of inspired by logic systems. And you can categorize them as expert systems. And what the characteristics of these were that they relied on hard-coded knowledge. Basically, teams of brilliant researchers and programmers, along with domain experts, would distill knowledge about a particular domain down to a set of rules, sometimes very complex rules and heuristics, and they would program those rules and heuristics directly into the machine. And so in effect, they were solving the problem and then programming that solution directly into the computer. The problem with these expert systems was, it turned out, is of course they can't then deal with the unexpected. If they come across something, say in the real world, that their programming did not prepare them for, they basically catastrophically fail. There's no way for them to deal with the unexpected. And the other thing that I'll come back to several times during this talk is this idea that if these systems would then be limited by the knowledge that we already have as human scientists and programmers. Obviously, if we're going to pre-programming these solutions, we have to know what these solutions are ahead of time. So there's an interesting limitation to what these systems might be able to do. Now, what's been happening in the last decade or more is the popularization and the sort of power of these learning systems have now become apparent, the sorts of systems that we build at DeepMind. And the idea behind these systems, which are often inspired by neuroscience and the way the brain achieves cognition, is that they learn directly from first principles. They learn solutions directly from raw data. So in effect, they learn for themselves the solutions rather than being pre-programmed with them. And the interesting thing about these learning systems is that they can potentially generalize to new tasks and come up with novel solutions, potentially even solutions that we, as the creators of those systems, don't know how to solve. That's the kind of exciting promise, if you like, of these types of systems. Now, behind our learning systems are two main techniques. One is deep learning, which many of you will be familiar with, which is neural networks, which is all the rage right now. But another area of machine learning that we focus in on is called reinforcement learning. And that's something that DeepMind really specializes in. And you can think of reinforcement learning as a sophisticated version of learning by trial and error, solely from rewards or punishments that you get back from the environment that you're interacting in. So for those of you not familiar with reinforcement learning, I'm just going to quickly explain it with a simple diagram. If you imagine on the left-hand side here, the agent, the AI system, we call them agents internally at DeepMind, and the agent finds itself in some form of environment. Now, if the environment is the real world, then the agent might be something like a robot, a physical robot. But also, we use a lot of simulations and virtual environments, in which case the agent is like an avatar, a virtual avatar. And the agent finds itself in this environment, and it's been set some kind of goal. So it's got to achieve a goal in that environment. And there's only two ways the agent really interacts with the environment. The first thing is through its observations, through its sensory apparatus. So we mostly use vision, but you could use other modalities, and we're exploring other modalities now, like audition and touch. And so you get these observations every time step, and it includes any rewards that might be coming from the environment. And the first job of the agent system is to build a model, a statistical model of the world out there, as accurate as possible, based on these incomplete observations. And once it has a model like that, the next job of the agent system is to pick the best action from the set of actions that are available to it at that moment in time. And it needs to pick the action that will best incrementally get it towards its goal. Right? So the agent has a model of the world. It can use that model to do planning, to think about what might happen and counterfactuals if it undertook certain actions. And then it can decide and evaluate if the end state that it's predicting it's going to get in will be a good state that will get it towards its goal. And usually these systems work in real time normally, so they have a certain amount of thinking time, and then they have to output the best action that it's found so far. That action gets outputted, and then that may or may not make a change to the environment, and that drives a new observation which the agent gets. So this whole system goes round in a cycle, and over time, the agent is an active learner. So the actions it takes drives the kind of experience that it will get in the future and what sorts of experience it can learn from in the future. So we think a lot about active learning and the agents themselves participating in their own learning by the actions they choose. So this is reinforcement learning. This diagram is pretty simple, but there are a lot of very complex mathematical complexities, challenges that need to be solved for us to make reinforcement work really well at scale. But we know that this kind of system is enough for human-level general intelligence, potentially, because this is what the human brain uses, one of the mechanisms we use to learn. And in fact, it's the dopamine system in the primate brain that implements a form of reinforcement learning called TD learning. So we know in the limit, this must be sufficient. This kind of system should be sufficient for general intelligence. So our first big result at DeepMind that many of you may be familiar with is back in 2013, we applied it for the first time, this kind of system. We combined deep learning with reinforcement learning, so this is called DeepRL, to a set of Atari games, classic Atari games from the 80s. And what we did is we trained a neural network here on the left with reinforcement learning based on the score that the system was achieving in the Atari game. And just from the pixels on the screen as the only inputs, it's not told anything about the rules or the controls. It has to learn all of that from first principles. It learns to maximize the score, and in the end is better than any human player at these Atari games. And this is really the first example of an end-to-end learning system that starts from raw pixels all the way to actions and decision-making in one system on a very challenging task like Atari games. The next thing we did was probably our most famous piece of work is we scaled this up, as Robert was alluding to the game of Go. I'm sure many of you know how to play Go here, but this is a Go board, picture of a Go board midway through a game. And Go is what effectively they play in China and Japan and Korea instead of chess, where it sort of occupies the same kind of intellectual niche as that. And it's thousands of years old, so it's the oldest game that's being continuously played by humans. And its complexity is many, many orders of magnitude more than chess. In fact, one easy way to just sort of illustrate that is there are 10 to the power 170 possible board configurations, so way more than there are atoms in the observable universe. So there's no way you could solve Go by brute forcing the solution and exhaustively searching all possibilities. So we have to do something a lot smarter and a lot more efficient if we want to crack a game like Go. Now, I'm not going to talk much about AlphaGo in this talk, but if you want to hear more about, if you're interested to see what happened to AlphaGo behind the scenes and our kind of once-in-a-lifetime experience we had playing the world champion Lee Sedol in Seoul, then I can recommend this award-winning documentary that shows what happened during the AlphaGo project. But what I would like to spend a lot of the talk today talking about is if that works, is our latest incarnation of AlphaGo, the kind of AlphaGo project, which we call AlphaZero. And I'll just put into context AlphaZero, how we evolved to this point over the last 4 or 5 years we've been working on this project. So first of all, there was AlphaGo. Now, AlphaGo learnt for itself how to play Go, but initially, what we did is we bootstrapped the algorithm with firstly initially mimicking the behavior of reasonably strong human players. So the bootstrapping of AlphaGo started by downloading several 100,000 games from the internet, Go servers, and training AlphaGo to mimic what the human players were going to play. And once that got reasonably good, so it was sort of the level of, an average club player, then we started the system of self-learning. So then AlphaGo, that version played against itself millions of times and learned from its own mistakes and improved itself incrementally through self-play. So that was the first version of AlphaGo that ended up beating the world champion Lee Sedol in 2016. Then we've created a version called AlphaGo Zero. So in this version, what the zero refers to is that we wanted to create an AlphaGo system that relied on zero human knowledge, domain-specific knowledge. So we wanted to remove this bootstrapping component of having to rely on the human games first, these amateur games first, to bootstrap us to the beginning level of the self-play system. And what we managed to do with AlphaGo Zero is actually create a system that started from random play, totally random play, and then learned for itself literally from first principles with no human domain input to become even stronger than the original AlphaGo. So that was the next step. And then finally, and you can see along the bottom axis here, this x-axis, is increasing generality. So this is what we were after. We were, firstly, could Go be done at all? And AlphaGo, by many experts, proclaimed that it was about a decade before they were expecting, both from the Go world and the AI world. So that was a huge challenge in itself, producing AlphaGo. And then we wanted to continually make it more general. So first, we removed the game-specific components from AlphaGo to make AlphaGo Zero. And then finally, at the final step, we created AlphaZero, which was now generalized to any two-player game, perfect information game. So not just Go, of course, but all the other two-player perfect information games. And it learns to play all of them from scratch in this same way, starting from randomly playing, randomly making moves, and then building up, finding some signal in that, and then incrementally improving. So funnily enough, although we cracked Go with AlphaGo, what did we want to test AlphaZero on? Obviously, we tested it on Go, and we made sure it was at least as strong, or in fact stronger than AlphaGo was. But we also wanted to show it could generalize to these other games. And we actually went back to chess, which, as all of you know, has a long and storied history, the connection between chess and AI, probably as old as the AI field itself. And all, my favorite sort of luminaries from the beginning of computer science, including, of course, John von Neumann, all had a go at writing chess programs. I think Alan Turing famously, he had a handwritten out chess program because there was no computers that could execute his program. And Alan Turing was the computer himself. So he executed the algorithm and he was able to, I think, beat a beginner player, which he was very pleased about. I think it took him a whole day to execute the program. So this has been a long and storied history. And in fact, Kasparov calls chess a Drosophila of reasoning, which I think is quite a nice phrase, and I think is true. And obviously, you might think, well, chess, why are we looking back at chess? It's been solved already. It's been cracked 20 years ago, famously by IBM's Deep Blue machine that famously beat Garry Kasparov back in 1997. And obviously, that was a huge watershed moment for AI. And I remember watching this match. I was at Cambridge as an undergrad at the time, and it was fascinating for me as both a chess player and an AI practitioner to see this happening. But I was left actually a little bit disappointed from this match in the sense that obviously it's an amazing technical achievement, but I actually came away more impressed by Garry Kasparov's mind than I was of the computer. Because here is Garry able to compete with this brute of a machine, a supercomputer. And of course, Garry can not just play chess, the best in history, but he can do all sorts of other things with his mind. Talk many languages, do politics, tie shoelaces, that obviously Deep Blue had no idea how to do. And the interesting thing is, and it just shows you there was something missing maybe from these kinds of expert systems that we would regard as the essence of intelligence. Deep Blue could not even play a strictly simpler game, say like tic-tac-toe, without, obviously much, much simpler than chess, without entirely being reprogrammed. So nothing in the Deep Blue's programming or to the system would be useful for even a much simpler game, strictly simpler game like tic-tac-toe. So it feels like there was something missing, and this was stuck in my mind for a long while, this idea of generality and flexibility, which I think are the hallmarks of general intelligence. And since 20 years of development has continued in chess computers, chess engines, and now they're phenomenally strong, obviously. The latest chess engines, you can get them on your mobile phone, and they're stronger than the human world champion. And the current strongest program is called Stockfish. It was also the strongest in 2016 when we were running our tests against AlphaZero. And the thing about these new generation of chess engines, they're all built on the same principles as Deep Blue, and they have thousands now of handcrafted heuristics and rules. So here's an example of just some of the rules that are in Stockfish. All sorts of rules about pawn structures and endgame databases and opening moves, and basically every single piece of human knowledge we think we have about chess, they've tried to encapsulate it in the forms of heuristics and rules for this program. But what we propose is, instead of these thousands of heuristics, we just replace it with two algorithms: self-play reinforcement learning allied with Monte Carlo tree search. That's it. So we just delete all of these thousands of rules, and we just have these two general principles. So I'm just going to explain to you a little bit of the training loop now with AlphaZero. And actually, it's what I'm going to describe as a hybrid of AlphaZero and AlphaGo Zero. They're more or less the same way we train it, but just for time's sake, I'm just going to explain in one go. And this is a lot simpler than the original AlphaGo program. So we ended up, so by making it more general, we also simplified the algorithm and streamlined it, which often happens in engineering disciplines. Once you understand how something works, you can kind of reverse engineer it and then rebuild it in a much more elegant way. So what we do actually is we train a neural network, and we used to have 2 neural networks, but now we have 1. And that one neural network has to predict 2 different things as outputs. One is a stack ranking of the most likely moves a human professional would make in that particular position. We call that the policy network. And you can think of that as reducing the search width that you have to do to find the good move, next move. Right? Instead of searching all of the possible moves, you can rank them in sort of probabilistic order. Then the second thing, which is probably even more important, is what we call the value network. And that is a neural network that outputs the evaluation of which side is winning, black or white, and what's the probability of winning. So that's really critical to obviously picking what is the best move in the current position. And it's that value network that in Go was much harder. No one had ever been able to hand program that in the way that you can in chess. And the reason that is because Go is a much more esoteric game. So even the top Go players can't really tell you in specific rules what kind of thought process they go through to evaluate the game. It's much more a game about intuition than it is about brute force calculation, say, compared to chess. So in fact, in Asia, Go is considered to be kind of like an art form. So here, with AlphaZero, we sidestep needing to do that, and we just get the system to learn for itself what are the right factors that need to be used to evaluate a particular position. So that's the structure of the neural network. What we do is, in batches of about 100,000, we have the current best version of the neural network, the current best, strongest version of the system, plays against itself 100,000 times on our servers at Google. And that generates a whole new rich data set, right? Self-generated data set. And what we do from that data set is we train up a new neural network, a new version that looks at that training data, and it tries to learn from the mistakes that led to losses, or it tries to learn from the good moves that led to wins, and it updates these 2 networks, the policy network and the value network. And then what we do is we take that new neural network and we play it against the old neural network in a kind of mini tournament, maybe 100 games or possibly 1,000 games, and we set the threshold to be 55% win rate, to be kind of significant win rate. And once it reaches that, then we replace the old network with the new one, and now the new network, the new improved one, plays the next 100,000 games and generates a new set of data, presumably at a slightly higher level of playing. Alternatively, if the new network can't beat the old network, we throw away the new network and we can continue, we play another 100,000 games with the old network, right? So now you have 200,000 games to learn from, and so on. And so eventually, sometimes some of the epochs take 1 million games, you eventually get a new neural network that can beat the old one 55% of the time. And this just continues round in a circle, and with AlphaZero, after 4 or 5 years of developing this, this is all completely automated. So you just press a button and it just does it. And you don't even need any researcher in the loop. So this is what we evolved the system to eventually. So then how did we evaluate it? Well, with AlphaZero, we played it against the current world champion of the traditional chess engines, these handcrafted, exhaustive search systems, of which Stockfish 8 was the current world champion. And we played a 1,000-game match, and AlphaZero won 155-6, the rest being draws, which is obviously an absolutely incredible margin at these levels of chess playing. And what's incredible is that AlphaZero got stronger than Stockfish after just 4 hours of training. So what you can see at this graph here, this performance graph, is starts at randomly playing. So it's literally like, randomly making moves. And in 4 hours, it's the strongest chess playing entity there's ever been in the history of the world. So, and you can actually watch it evolving. So in real time, as you watch this, you sort of set it off at lunchtime, come back at tea, and it's stunning. So, you know, you can't help but sort of be quite astounded by that, and especially for me, this is like, you know, I used to play, as Robert said, I used to play chess. I play Go a bit as well, but I play chess a lot stronger. So I could almost viscerally feel this optimization process happening in some way by comparing it to what I know about chess. So it's quite a mind-blowing experience, actually, just watching this system train. And just to prove it really was general, we tried it on a third game as well called shogi, which is Japanese chess, which is very different from Western chess, but also played professionally to a very, very high standard in Japan, and for many hundreds of years of history as well in that game. And our same system beats all the strongest other programs in these other games after just a few hours of training, the same single AlphaZero system. So we believe that actually, although we tried it on 3 games, we believe actually that this system could play any 2-player perfect information game to extremely high level, out of the box, with some training through self-play. So that's the raw results, but there are some other really interesting features about AlphaZero. One thing is, just to show you that this is not just down to brute force search. If we compare the state-of-the-art chess engines today, like Stockfish, or the ones that you can just buy and sort of freely available, they search the order of tens of millions of moves per decision they have to make, per move they have to make. So that's what they do. Of course, if you compare that to what a human grandmaster does, they only look at maybe the order of hundreds of moves for each decision they need to make. So why are they able to be even competitive compared to the chess engines? It's because human grandmasters have way better evaluation functions than chess engines, which have very weak evaluation functions, but compensate by doing a lot of search. And if you look at AlphaZero, it's sort of right in the middle here. It's not as efficient as human grandmasters, so AlphaZero looks at around tens of thousands of moves per decision, but it's way, way more efficient, 1,000 times more efficient in terms of search than the chess engines, the traditional chess engines. So it's, you know, inching towards, on this spectrum, towards the way that human players play the game. The other exciting thing from a chess point of view is that not only was AlphaZero extremely strong, it actually came up with a new style of chess. And I haven't got time to sort of go into this, but the headline summary is that AlphaZero really likes dynamic attacking chess, and this can be encapsulated in the idea it prefers mobility of its pieces versus materiality, the number of pieces that it has, which for people who know about chess engines is kind of mind-blowing, because one of the things traditional chess engines do is they grab pieces and material. They love material. And the reason they do is because they have inbuilt rules telling them that, you know, rooks are 5 points, knights are 3 points, queen is 9 points. And actually, one of the first heuristics you would program into any chess engine is the player that has more points on their side, if you add up all the pieces, is generally in the lead, generally has a better position. But of course, AlphaZero has no notion of these hard-coded levels of worth of these pieces. So it's free to make its own decision about what is valuable in a particular position. So, so these interesting properties of AlphaZero are the crux of AlphaZero's strength. It is better evaluating positions than chess engines are, traditional chess engines. And the reasons are, which I've already alluded to, is that it doesn't have to overcome inbuilt rules. So these inbuilt rules that we spent the last 20, 30 years handcrafting and distilling from human grandmasters might be getting in the way, in some sense, of more creative play that these machines could come up with. It's also better at balancing different factors. If you think about it, one of the complications of a program like Stockfish is that not only do you have to come up with the right 1,000 rules, but how do you balance them against each other, right? How are you going to weight them all together? And that's a real art form, but also it's an extremely difficult optimization process. The other thing that AlphaZero can do is it can be dynamically evaluated. And what I mean by that is it can take into account the context of the current position, the specific situation it's in. It can sort of decide that, in this case, this asset, my rook, is not as valuable as my opponent's knight that might be in a really strong position, outpost in this position, and I can decide to sacrifice it. I don't have to overcome this inbuilt idea that it's -2 points if I do that. One other thing to point out as well is that these systems, chess is also phenomenally complex, not as complex as Go, but incredibly complex. You can't just brute force it all. And this is not just a question of interpolation or memorization. It isn't just memorizing all the positions it's played. It doesn't have the capacity to do that of these millions of games. And also, when it plays new games against human masters or other programs, obviously it has never been in those positions before. So it really has to extrapolate the knowledge it has and generalize to these new positions. So it's not something as simple as just memorizing everything it's seen. But of course, although AlphaZero and AlphaGo played very creative moves within the limited domain of those games, I would not say that it's somehow creative in the fuller sense of that word. And the obvious way to illustrate that is, whilst it can play creative moves within these games, none of these systems can invent chess or invent Go yet, I should say. So that's still, unknown how we would get out these kind of AI systems, how to do that. So if you're interested more in AlphaZero's chess style, then actually the 2-time British champion Matthew Sadler and Natasha Reagan wrote this great book, Game Changer. It's a kind of best-selling chess book at the moment, and encapsulating 7 principles they found that AlphaZero was using in its style that they felt other chess players could benefit and learn from. And we've seen some of the world's top grandmasters now using some of these motifs, including Magnus Carlsen. I know he's read the book and is interested in it. And on the other side is AlphaZero. If you're interested in the architecture, then you can look at our recent science paper on that. And I'll just close this bit of it by this section by just giving you this quote from Garry Kasparov, who wrote a nice op-ed for Science to go with our science paper. And he mentioned that programs usually reflect priorities and prejudices of programmers, but because AlphaZero learns for itself, I would say that its style reflects the truth about the game, which is a kind of incredible statement coming from Garry. I think he was also partly influenced because he said the style reminded him of his play, so perhaps there was a slight bias in what he said here. And we've then further extended it. I haven't got time to go into this today, but one of the criticisms of this work is that, board games, of course, Go is very complex, chess is complex, but at the end of the day, board games themselves have simple state transitions, and you have perfect information. Can these types of systems really work in where you have hidden information, partially observable environments, you have massive action spaces, and you need things like long-term planning? And we believe systems like AlphaZero can extend to that. And we've done the first steps towards that by playing computer games, real-time strategy games like StarCraft 2, which is probably the most complex real-time strategy game there is ever been invented. And we recently created a system called AlphaStar that was able to beat top professionals in this game 10-0 and do things like find out information for itself. So these are, I think, promising extensions that show that these systems can be even more general than 2-player perfect information games. But having said all that, these are big accomplishments, but there are many key challenges that remain. In fact, this is one of the most exciting times, I think, to be in AI. I feel like we've done a lot of the preliminaries, but there are so many open questions. Here are just a bunch of them that I think about a lot that remain to be solved, from unsupervised learning to memory to learning abstract concepts, and of course, going up the ladder of human cognition to things like symbolic reasoning and language understanding, which none of our current systems are able to do. So I'm just going to switch gears a little bit now and talk about some of our other work where we've been applying these types of technologies. Now, the thesis behind DeepMind was to use games and simulations as a perfect kind of proving ground for developing AI. It's very efficient to develop them within these virtual environments. But at the end of the day, the idea is to create general algorithms that will transfer to real-world problems and tackle some real-world problems that have a lot of impact. And what's exciting now is that I think our algorithms are starting to become mature enough now that we can potentially apply them to some useful places. There's lots of commercial applications. You'll have read about many of them. We've applied this within Google and externally on lots of areas, from healthcare to energy optimization to Android phones, saving battery life of Android phones, to voice synthesis with our WaveNet system. But what I really want to talk about today is not these kind of more commercial applications, but something that's really my main passion and the reason I work on AI, and I think most appropriate for this audience, is using AI to accelerate scientific discovery itself. And AI itself has a long way to go. I just gave a slide of some of the unresolved problems still that remain to be solved. But the current systems, AlphaZero-like systems, I believe already could potentially be applied to quite a few interesting areas of science. And I think it can be applied to, these kinds of techniques can be applied to any problems that have this kind of character. So one thing we look for is the kind of nature of the problem is a search through massive combinatorial space. That's good kind of problem structure for our systems. Second thing you need is a clear objective function or metric to optimize against, so you know you're going in the right direction as you're hill climbing or searching. And then thirdly, you either need lots of ground truth data or an accurate and efficient simulator. And ideally, you have both. But we specialize actually in situations where all you've got is a simulator, and then you have to generate your own data to learn from. So if these three things sort of hold about your problem, then potentially this kind of intelligent optimization process or intelligent search process that AlphaZero represents could be appropriate to be applied to that kind of problem. And DeepMind, over the last couple of years, we've started our own science team, multidisciplinary science team, and we're growing that. And we are now starting to look at many problems in collaboration with friends of ours in academia, in all sorts of a very diverse set of different areas that we feel have some very important problems, impactful problems that fit those criteria. So quantum chemistry, protein folding, in health like retinal disease detection from retinal scans, and also some areas of mathematics and theorem proving. So we have lots of interesting work going on in all of these areas and others besides. But I'm going to spend the rest of the time just talking about what I think is our most exciting breakthrough of last year, which is our work in protein folding. And we call this system AlphaFold. And proteins, I'm sure most of you are familiar. We can think of them as incredible, exquisite molecular machines. Life depends on proteins, and here's a mitochondrial ATP synthase that kind of generates ATP, which is the energy our cells use. There's another one on the right-hand side. Here's a calcium pump. So these amazing molecular machines that do all sorts of things in our body. And so what is the protein folding problem? Well, in essence, you start with an amino acid sequence of bases on the left-hand side. And what you need to do is, based on that sequence, that 1D sequence, can you predict the 3D structure of the protein here on the right-hand side? And this is hemoglobin, and you can actually see the little hole here for the oxygen to be carried around. And so what we would like to know is this 3D structure directly from this 1D sequence of amino acids. And this is an extremely hard problem, and it's been one of the kind of grand challenges in computational biology for many decades. And if we could solve this problem, it would help with disease understanding. Many diseases are thought to be due to the fact that proteins misfold or in some way are involved. And drug discovery, because a lot of drugs, what you would do to design the drug compounds is target the kind of the outside of the protein where the receptors are. And then synthetic protein design, actually generating or modifying proteins for specific purposes. So our system was set up like this. AlphaFold, we trained a neural network through supervised learning. There are around 15,000 to 30,000 protein structures already known through painstaking crystallography. And they're all in a big database. And what we did is we trained a big neural network to take in the amino acid sequence, augment it a bit with other parts of data I haven't got time to go into, but we augment it with lots of random amino acid sequences that we know of and we've collected from nature, but we don't know the structure from. But there's ways of augmenting our relatively small amount of data with that. And we also know the structure of these 30,000 proteins. So we know the structure, we know the amino acid sequence, and what we do from the structure is we reconstruct the angles of each of the amino acids, base pairs, and we also get a histogram, which is a histogram of all the pairwise distances between the different base pairs within that huge amino acid sequence. And both of these two, the angles and the histograms, are distributions. And so we train this in a supervised way for this network to output the right distributions for these amino acid sequences for these known 30,000 protein structures. And then once we've done that, obviously we can now give the system a new protein that it's never seen before, a new amino acid sequence that it's never seen before, and ask it to predict the 3D structure. And what we do is we just use, actually in the end, a fairly simple numerical optimization process. We take the estimated angle distributions that come out of the neural network based on this new amino acid sequence, and we initialize it. We make a sample from the distribution, and then we kind of get a score as to how good a score is that in terms of energy with these angle settings. And we also can calculate a histogram from these angle settings, and we also get a score from that as to how well does it agree with the kind of predicted histogram from the neural network. And then finally, to compute a total score of how well this fits, we also have this thing called a van der Waals score, which comes from basic chemistry, and that just makes sure that the amino acids and the molecules involved aren't put on top of each other in ways that would not be possible in physical chemistry. So these three kind of scores are all factored together into a total score, and then you just optimize this. We tried all sorts of different methods, neural network, simulated annealing, but actually just a fairly standard Newton methods work very well here. And then you end up with a predictor structure. So here, I think the green is the predicted, the blue is the ground truth. And then you compare it to what, if you have the ground truth, you compare the predictor structure to the ground truth. So this is what it looks like. You start with this is a protein that's sort of unfolded, the basic starting structure, and then you run this algorithm, and then over many time steps, takes a few hours this, it kind of jigs it around, and then you finally get the final predictor structure that it outputs. So once we train this system, we entered it into what's sometimes called the Olympics of protein folding. It's called CASP. It runs every 2 years. It's a really cool competition because they get input from labs around the world who are doing crystallography and other methods to actually find the structures of important proteins. But they collect the unpublished ones, so they've been sold but they're not been published over the previous 6 months. And then they release one to you. There's about 80 that they have, and they release one target a day, and they give you 3 weeks to give back a predicted structure. And then at the end of a few months of the competition, this was happening last summer, they then publish all the results, all the ground truths, and then they can see which teams did well on all the different amino acid sequences. So there's hundreds of sort of research teams from around the world compete in this every 2 years. And so this is some of our predicted folds, and you can see that they overlap they agree very well with the ground truth. And in fact, our system was the most accurate predicting structures for 25 out of the 43 proteins in the hardest category. And for comparison, the next best team had the most accurate structure for 3 out of the 43. And so we won this competition, but we also won it by quite a large margin. So this is the sort of standardized score of all the teams, and that's us in purple. And so it's quite a big, it's like about 30% above the second scoring team, or 25%. So there was something different in nature, in character of what the systems we were trying to use. Now, we're state of the art, but I have to be clear, we're still a long way from solving the protein folding problem. Biologists tell us that we need to be within 1 angstrom accuracy for it to be biologically useful, and we're still around, on average about 3 angstroms out. So we're still exploring, we're working hard on this still, and we're exploring many other techniques, including end-to-end folding, rather than sort of Newton methods for that final step. So I just want to finish now, before we go into the Q&A, just talking a little bit, sort of a higher level about the philosophy of what we're doing, which is something I think about a lot. And one of the ways I describe our mission is we're trying to find or trying to build a meta-solution to solve other problems. One of the things I sort of see confronting society today, but all of us as scientists as well, is just the huge deluge of data that we all have, like information overload that we're generating all the time from all of our experiments. And also, potentially the complexity of the systems that we're trying to understand now and master, whether that's, macroeconomics or climate or some complex disease process. These are really huge challenges that even the smartest people or teams of the smartest scientists and experts in the world are finding it difficult to make progress with. Another thing is that I guess the buzzword in industry of the last few years is now AI, But of the last decade, the kind of early 2000s, it was big data. And I think, in a way, big data is the problem. And everybody's got big data, right? All companies do, all of you do as scientists. But the question is, how do you find the insights or the structure in that data? And I think AI is potentially the answer to that. Another way I think about intelligence is, this kind of intelligence is, you can think of it as a kind of process an automated process that converts unstructured information into useful, actionable knowledge. And I think it'd be incredible if we have more of this, this kind of phenomenon or process around routinely to help us in our work. And my dream has always been, since I can remember, is to try and make AI-assisted science possible, and for us to accelerate all the discoveries that we're trying to make at the moment, and society, I think, desperately needs. So it's a very exciting time right now in AI, and I think AI holds enormous promise for the future. But just on a note of caution, of course, AI, just like any other inherently powerful technology or tool, has to be used and built responsibly and ethically, and for the benefit of everyone in society, not just a few people or a few companies. And we strongly believe that at DeepMind, and that's been our philosophy from the founding of the company. And a lot more research and discussion is needed with not just scientists, but society at large and other stakeholders to make sure that this happens. And we've been doing our part on that. We have a kind of mini think tank at DeepMind called Ethics and Society, DeepMind Ethics and Society. And we've also helped stand up an industry body called Partnership on AI with all the other big companies to think about these questions. And I just want to leave you with this thought that I've had as a neuroscientist, is that there are many sort of profound mysteries of the mind, like what consciousness is, the nature of creativity and dreams and other things. And I do think we're on a really exciting scientific journey in that if we can kind of distill AI and intelligence into an algorithmic construct, we may be able to kind of compare AI with the human mind and therefore better understand some of the unique properties of the mind by making that comparison. So I just want to leave you with Richard Feynman's quote, "What I cannot create, I do not understand," and I really believe that in the scientific work that we do here. So thanks for listening, and I want to just thank all my amazing team who've worked on all these projects that I've just discussed at DeepMind. Thank you.